Okay, so hi everybody, thanks for coming. We have today happy to have our own Itai. Itai is an expert in high energy transient phenomena and dynamical processes occurring near supermassive black holes, center of galaxies on gravitational wave sources. He got a PhD in Hebrew University of Jerusalem as an Adams Fellow, and now he's a member here. And also at the theoretical high energy astrophysics group at Columbia University. And also I must say that Itai also worked a bit in biophysics in past life, let's say. We're happy, but today we're happy to have him here talking about quasi-periodic eruptions and stellar destruction in galactic nuclei. So please, Itai.
Okay. Hi everyone, thank you all for coming. Thank you, Giovanni, for this introduction. So, yeah, as the title reads, today I'll be telling you about quasi-periodic eruptions, which is a new observational phenomena of bright X-ray flares observed in centers of galaxies near their supermassive black holes. So I'll try to give you an overview of the current observational understanding of this phenomenon, and then I'll describe a new model, which we are yet to publish, where we think we have some understanding of the different properties of this new observed phenomenon. So I'll start out with a very brief context and motivation. So as I said, quasi-periodic eruptions or QPEs occur around supermassive black holes, and as such, they may provide us with an additional tool to study these objects. So for this crowd, I don't need to motivate why black holes are interesting, but I just listed here a few different questions which we may be interested in answering eventually. And to get this discussion going, I'll just perhaps shortly dwell on this question of how do black holes form in the early universe. So as you know, there are two possible scenarios that are being discussed in the literature about the formation of supermassive black holes in the early universe. So one possibility is that the current supermassive black holes that we're seeing were seeded by the direct collapse of massive gas clouds that formed black hole seeds of about 10 to the 4 solar mass that eventually merged and accreted to form the current population of black holes. And the other alternative is that the seeds were actually much smaller and were formed by the remnants of the first population of massive stars in the universe that's undergone core collapse and formed black holes of about 100 solar mass. So these two pictures give different predictions or observational implications regarding the occupancy fraction of black holes and low mass galaxies in the current day universe. So in the case of death of massive stars, you would expect that nearly all galaxies of 10 to the 9 solar mass should host a black hole of about 10 to the 5 solar mass black holes. And on the other hand, for the direct collapse scenario, only about half of such galaxies would host a black hole of this mass. And the issue is sort of seen in this plot of the black hole mass versus the M sigma plot updated from a few years ago, where you can see that to answer this question, we are mostly interested in black holes of this mass range of about 10 to the 5 solar mass, which, as you can see, is very sparsely populated with essentially only upper limits in this range. And the reason is that these low mass supermassive black holes are essentially quiet. They're hard to observe, hard to detect, because they're not accreting large amounts of mass as AGNs in the much higher mass range. And essentially the only way to actually probe their mass is through the dynamics of the stars very close to them within their radius of influence. But because they're small and far away, we're limited by angular resolution, and direct measurements of their masses and properties are limited. So we are facing this problem that if we want to observationally constrain these different scenarios, we're limited by our lack of ability to say something about these populations. And that sort of gives the motivation or the hope that by studying transients that occur around these otherwise invisible population of supermassive black holes in the low mass range, we may be able to constrain these different questions that I listed before. So this is part of the motivation why we should study events like QPEs or tidal disruption events. So the focus of this talk is going to be about QPEs, but just for the context, and since I'll be referring to tidal disruption events later on. So yes, tidal disruption events, just as a reminder, occur when a star passes close to a supermassive black hole in a highly eccentric orbit, is then being stripped apart by tidal forces. About half of the stellar material remains bound to the black hole and falls back onto it, leading to high accretion rates that produce a bright flare. And we're currently seeing these events or candidates of these events in a broad range of messengers, from X-rays to radio, UV, even recently neutrinos. And these events can sort of give us a handle on this unseen population of supermassive black holes. And QPEs, which I'll now present, may provide an additional handle onto these populations. So I'll start off by explaining what do we know about this new phenomenon from the observational point of view. So I'm not an observer, so I'll try to do my best to convey the current understanding, but yeah, feel free to ask questions and I'll try to shed more light on any question you may have. So as I said at the beginning, QPEs, these are bright recurring X-ray flares that occur around centers of distant galaxies. It's a fairly new phenomenon. The first QPE was identified in late 2019. And since then, there have been 4 systems that have been confirmed. I wrote here plus 2.5 because, well, this is sort of rumors that I recently heard, but there are possibly 2 additional sources that are yet to be confirmed. And the 0.5 is this one system where we only have 2 flares or even 1.5 flares. So it's kind of hard to say whether this is a recurring phenomenon as the common QPEs. What characterizes them is that they have recurrence times of order hours to up to a day, depending on the system. They're pretty bright in the X-rays. Their peak luminosities of order 10 to the 42 or even a few 10 to the 42 ergs per second. And the corresponding peak temperature at the peak of the flare is of order 100 to 200 electron volts. And they seem to occur around supermassive black holes with fairly low masses, maybe a few 10 to the 5 to a few 10 to the 6 solar mass. But this is still, you should take this figure here with a grain of salt because this is sort of based on these very rough scaling relations that do not really work well in this low mass range because of the reasons I mentioned before. The flares themselves have duty cycles, meaning the duration of the flare compared to the recurrence time between consecutive flares, which is of order 10% or maybe even 30% in the example showed here. And I'll now dive into a bit of more details. Yes.
Do they just keep on going, or is there like a period where you see 100 and they stop? Switch on again then?
Yeah, that's a good question. So part of the problem in studying these events is that these dedicated X-ray observations are quite expensive. We don't have many instruments that are actually capable of doing these very extended time series. So I'll mention in a few more slides what do we know about the duration of these events, how long do they actually last, their lifetime. What we can say, and again, because it's a fairly new phenomenon, we've only been knowing them for a few years now, so it's hard to tell whether they last a century or a decade or less. But I'll get back to that. It's a good question.
These ones, if you point again, they're still doing it. The ones that, or are there some that they have gone away?
Okay, so yeah, these are great questions. So at least some of them that have been followed up recently are still there. So, you know, maybe they're gone by now, but I think within the last half a year or so, they're still there. There is one example of a system that was actually detected in archival data. They were searching for something similar in the archival X-ray data, and it seemed to be flaring about a couple of decades ago. And then when it was searched again, sort of in light of this new discovery, it was gone. So we know that at least for some systems, they're not super long-lived. But I'll sort of get back to this question of lifetime later on. Okay, so let's see what else can we say about their overall behavior. So this is an example showing the first QPE system that was detected, but I'm showing here properties that are sort of shared amongst all of the known systems. So you can see here the light curve of the flare, and the x-axis here is the phase. So one is the location of approximately the peak. And you can see this flare shown in different energy bands. I'm not sure if the font is large enough, but the blue band corresponds to the highest energy photon, so the hard band, and the red corresponds to the soft band. Here, the flares at the different bands are normalized to the quiescence, and here they're normalized to the peak, so they all share the same peak, and just the quiescence varies. And one thing that you can easily see from this plot is that it seems like these flare early at the hard bands and later on at softer bands, and also the fall time is actually faster for the hard bands and later on for the soft bands. So this is one feature that I will later try to address in my model, or at least get back to. You can also see here, and these two plots, this shows the phase folded light curve over several flares. And this is the corresponding spectra for different parts of the flare. So you can see that as we move from the quiescent level to the peak of the flare, the amplitude rises, so that's obvious, but also the temperature increases and then goes back. So the temperature increase is by about a factor of 2. And I should also mention that if you just try to assign a black body radius to this emission, considering the luminosity and the temperature, and it's taking luminosity divided by temperature to the 4th power. So actually the corresponding black body radius at peak is actually smaller than the corresponding black body radius at quiescence. So that's another sort of hint that we will address.
And what is that radius?
In units of Rg, say.
Say.
Yeah, so the quiescence sort of seems to be consistent with an accretion disk onto the black hole, so say a few Rg. And actually the radius at peak is, in some systems, inconveniently smaller than Rg. So maybe half Rg, but we don't know the black hole masses to a very high accuracy. So there could be a factor of 5 easily that's missing here. Yeah. And this is another sort of way to summarize this different behavior. I mean, the actual axes probably mean more to observers than to me, but here the x-axis is the hardness ratio. So that's the ratio of hard photons compared to the total number of photons in the band of the instrument. And on the y-axis is the count rate. But the general property here that I want to highlight is that as the flare goes on, it sort of forms this counterclockwise loop. And this is a general property of all the QPEs that are known. So it sort of points that this is indeed, although there are some differences between the different systems, possibly the emission mechanism sort of has a shared property. Okay, so as the name implies, they're quasi-periodic. And it turned out this is actually something that was sort of more appreciated in the last half a year or so, that there are possibly 2 classes of quasi-periodicity. So the first class, which occurs in 2 out of the 4 confirmed systems, is the one that I will refer to as the regular flaring system. That shows this very distinct behavior that can sort of be seen here, that flares are separated, alternating between short recurrence time to long recurrence time to short and long. So they're coming in pairs of long and short recurrence. So this quasiness is not really just some random noise, but there is some regularity to it. So this is going to be one very important clue in the model that I'm going to present. The other 2 out of 4 systems are these more erratic, highly irregular flaring behavior. So this is seen here. In the top 2 panels, you see the 2 regular systems shown in pairs of consecutive flares. So this is folded every 2 flares. And you can see that all the folded flares sort of follow this same pattern with the long, short behavior. And when you're doing the same for the other systems, you see that the flares sort of spread all over, and there doesn't seem to be a very inherent period to them. Yes.
So is there a reason, obvious reason to believe that the T1 and T2 is not just 2 different things that are happening with one period of T1 plus T2, but also?
You're saying, is it possible that what we're seeing here is just 2 purely periodic phenomena that are overlaid? Possibly. I don't think there is a good model that will sort of produce this behavior. We can go back to your question. I mean, I can come up with a simple model that will produce this, but then I will sort of have to argue against it on the grounds of rates. But when we discussed, what these things might actually be, I'll get back to that.
Even in the irregular systems,
Yes.
there could be a clock. That is, if one pulse is early, the next one is going to be late. Is there any evidence for that?
Can you perhaps
So
rephrase the
suppose
question?
they're precisely periodic,
Yes.
but there's a random lag forward and back from the periodicity.
Yes.
Does that fit the data?
Okay. You're asking about the irregular systems. Yeah. So for the irregular systems, at first they were also characterized with sort of a single mean period, which sort of seems right. This is, I guess, what you're trying to get when you do this folding. But then I think I'm not showing here the 4th one, which is even more irregular. It's even hard to assign a single period to it. I mean, if you look at, say 5 flares, then yeah, it sort of seems that maybe there's some super period and some scatter around it. But then, you might get, I don't know, a flare that comes at way too early. Instead of P, it comes at 0.1 P. Then it's kind of hard to explain this within one underlying clock. But it's a good question, and I'm already saying that the model I'm going to describe mostly tries to explain these more regular ones. I'm not so sure about the irregular ones, but we can discuss later how maybe they may also fit with this framework. Yes.
Is it just me or that in addition to this successive T1, T2, the amplitude seems
Yes.
to be
So this was my next point exactly. So this is shown here actually. I'll start by just saying something about this T1, T2. So here you can see what is plotted here as a function of time is the recurrence time between 2 consecutive flares, and you see this behavior of long, short, long, short. There may be some longer term modulation to it, but you can see this behavior at different epochs. In addition, it seems that at least in one of the systems, in addition to this long, short, there is also a correlation between bright and weak. So you can see here, there are weak flares and bright flares. And after a long bright flare, you get a long recurrence time and vice versa. And this is seen here and also summarized in this plot where this shows, well, the resolution is a bit low, but you can see here the recurrence time and the ratio of consecutive flares. And you see that, yeah, when you have exactly this behavior that I mentioned, after weak flares, you get a short recurrence time, and after strong flares, you get long recurrence time. This is possibly another hint.
Is this true for both of your?
The regular ones?
For both.
I think it's not as distinct in the second regular system. Yeah, but as we get more systems, we'll know whether this is significant or not.
It looks like those modulations are decaying.
Yeah, so this decaying sign is just something that they added for guidance. I think it's hard to say that this actually decays significantly, because I think then at a later epoch, you again get an amplitude which is similar to what you had here. But possibly.
You may have said this, but this time series in the top left, is that the full data run?
This?
Yeah.
No, it's one epoch of observations that I think corresponds to this. So for this system, this was the one that was detected in 2019. So there were some observations in 2019, and then maybe half a year later, and then another half a year. So yeah, these are different epochs. So this is not the full data that we have, but I would say that, here I'm showing 5 flares, maybe there are, I would say 30 flares or.
But these are each the full lengths of the epochs, or?
Yes.
Okay.
Yeah, that's, that covers, so for this system, the time between flares is about 9 hours. So you got, I guess 2 days of data. Okay, another interesting clue is this, apparently an association between QPEs and TDEs. So for at least some of the systems, it seems like QPEs appeared after what seems like a long-term decay in the X-ray flux from the system that is more or less consistent with what you would expect from the late light curve of TDE occurring in the system. So this is another clue. Here I'm showing the light curve with this roughly L goes as T to the minus 5/3, which is a general prediction for TDEs that preceded the appearance of QPEs in this system. I should also mention that this was actually how QPEs were first detected. So for this system, it was followed up. It was interesting because it showed this late time evolution that sort of seems like TDE, but then as they were monitoring it with X-rays, QPEs appeared. So possibly this is something that exists in other post-TDE systems that we just haven't detected yet. Maybe this is a coincidence, but again, the rates would sort of argue against it because TDEs are quite rare to begin with. So there may be some association between QPEs and TDEs.
So you're probably getting at this, but you said in 2 for sure. Which 2? Are they the regular ones, the not regular ones?
Yeah, so for sure in one of the regular ones. And then there is another more irregular one that also shows signs that are pretty obvious. It was again sort of, this was the one that was detected in archival data. And then one of them, the second regular one has some evidence, but is not as direct because we don't have good time coverage that goes before the appearance of QPEs.
Are there tidal disruption events that have been observed where we can rule out something like this, or do the timescales work out that we can't do that yet?
It's a good question, and I'm not sure. We should ask observers. My understanding is that, well, I'll get back to that.
So in TDE, people found that these TDE are more likely to be in post-starburst galaxies. How about QPE? Do people also found that association?
Right. Yeah, another great question. I think I even have a backup slide on that. There was some study that tried to analyze what are the properties of the hosts of QPEs. So as you mentioned, TDEs tend to occur in these post-starburst galaxies, these green valley galaxies. And there is some evidence that QPEs also tend to prefer these galaxies. So this is another sort of evidence for this association between QPEs and TDEs.
Only 4, so probably.
Yeah. I mean, everything, all the statements here are,
And 2 or 3
very.
is what is like that, yeah.
Yes, all this evidence is very, very, not strong, but we work with what we have. I'll just mention, so the main tool or the main promise for detecting more QPEs is are in general X-ray surveys like eROSITA. So eROSITA is an X-ray instrument that is located on the SRG satellite, which is a joint Russian-German X-ray observatory. So the Russians and Germans split the sky into two halves, two hemispheres. Germany got one hemisphere, Russia got the other, in terms of the data that will be collected. eROSITA scans the sky to eventually form this beautiful map of the X-ray sky. But as it does that, it passes on the same spot at 4-hour intervals for several epochs, and then moves on to the next one. There is some overlap in the tiling. Unfortunately, almost a year ago, Germany decided to switch off eROSITA because of the invasion to Ukraine. And yeah, they stopped all the scientific cooperation with Russia. We're not sure when will this change, but currently eROSITA is not collecting any data. So all these new systems that I mentioned come from analysis of data that was already collected more than a year ago. But we hope that in the future there will be more observations, but currently we're limited like before this happened. Because of the timing of the observations, as I said, 4 hours per point on the sky, you always need to have some follow-up with another instrument like XMM Newton or nicer that will give you this better time coverage. So they're first detected through something that looks like this. There is some excess with respect to the quiescence that appears to be periodic. Again, this is limited to the aliasing and the timing of this 4-hour observation, and then this is being followed up. So here I summarized the properties of the known QPE systems. Again, the numbers are not very important. It's just to give you a sense of the things that I mentioned, and we'll try to explain that. Okay, so theoretical model. In the last 3 years, I think there have been over a couple of dozen papers that try to explain this interesting phenomenon. I mean, I contributed 2 papers already, so and now I'm going to discuss something that will appear in a 3rd paper. And I have to tell you that I mean, I've worked on this for a while, and it's actually quite hard to come up with a consistent model that explains all of the observables, even to within a factor of a few, even at the toy model level. So, you know, I challenge you to come up with more models, but it's actually not that easy to explain all the observables for all the systems. I won't have time to go into the details of what other people have proposed, but I'll just mention that there have been sort of a few classes of models that have been discussed. Some people have invoked some forms of disk instabilities to produce these periodic or quasi-periodic flares. There have been ideas of lensing by a massive companion to the supermassive black hole as a source of these flares that we're seeing. And then a 3rd major class is models that involve some low mass companion to the supermassive black hole that is somehow responsible for producing these flares. And within this, there are two camps. One is the compact companion camp, where you have a white dwarf or a helium core of a stripped star that is responsible for producing these flares. And then the 2nd camp, which I'm a part of, which suggests that this is actually a main sequence star or a low mass main sequence star that is responsible. And the model that I'm going to describe now is sort of a combination of a few ideas that came about with different models, and I'm going to present it next. For a model to be good, there's a long checklist of things that you should satisfy, things having to do with the timing of the flares, the emission that we've discussed, and then all sorts of associated properties that tell us something about the environments in which these events occur. So the basic picture is actually summarized very easily in this cartoon picture here. Our idea is the following. Around the supermassive black hole, there is an accretion disk, and there is a main sequence star that follows slightly eccentric and inclined orbit with respect to the plane of the disk, and collisions between the star and the disk produce flares. I'll try to convince you why this can actually explain many of the properties that we discussed before. The quiescence between the flares is produced by the disk emission itself. And there will be some evolution of the flare timing due to precession, both apsidal precession and nodal precession, lens steering precession. And I will discuss now first this association between TDs and QPEs within this picture. So how do we make this association? The basic idea is again quite simple. If you were to have a star on the right period around the supermassive black hole, so undisturbed without the presence of an accretion disk, it will evolve over a long time scale. So it will eventually inspiral towards the black hole, but this will be over the gravitational wave time scale of about 1 million years. During this time, a TD is likely to occur. So TDEs occur about roughly once per 10,000 years. So the TDE will form this disk, and then the star, which was already there, will impact the disk and produce these flares. This very naturally explains this connection between TDEs and QPEs, if you agree that QPEs are indeed formed by this picture that we proposed.
What's the orbital radius compared to also the disk?
Okay.
That you need for this.
Yeah, so so this is set by the period, and this is something of the order of 100 RG or so. Again, depending on the black hole mass, but this is roughly the number. Okay, so perhaps let me first explain how do we think that you actually end up with stars on such orbits, on tight orbits around the supermassive black hole. So for that, I'll sort of show this cartoon picture of the processes that end up putting stars close to the supermassive black hole in centers of galaxies. So I'm showing here this schematic phase space of orbits within the radius of influence around the supermassive black hole. So the x-axis is the semi-major axis of the orbit, and the y-axis is the pericenter distance. So this is a good proxy for angular momentum. This is a good proxy for orbital energy. So the diagonal line here corresponds to circular orbits, and you need to assume something about the distribution of stars around the supermassive black hole. You can, for instance, take a Bochor-Wolff cusp, and that gives you some scaling of the number of stars as a function of radius. So there are horizontal lines that you can add here. One is the tidal radius, which is the point at which tidal forces exceed the star's self-gravity. So whenever an orbit passes this point, you get a tidal disruption, or mass is lost from the star to the black hole. And this sets the outer boundary in this problem, which is the radius of influence of order a parsec for 10 to the 6 solar mass black hole. So if you start out with a population of stars that are located at around the radius of influence, so that's where most stars are, and you let this population evolve, then relaxation processes, whether it be two-body relaxation or resonant relaxation, they will excite the angular momentum of these orbits. And in general, the angular momentum relaxation time for slightly eccentric orbits is shorter than the relaxation time in energy. So you get these vertical trajectories where stars roughly maintain their semi-major axis and their pericenter distance diffuses up and down along this line until they occasionally cross this line, and then you get a tidal disruption event. So that's a very simple picture of how most TDEs are formed. But then there's another line that you can add here, which is the line that delineates this phase space into regions in which relaxation processes like two-body scattering dominate versus region in which gravitational wave timescale is actually shorter. So if you start out with an orbit that is slightly smaller than the radius of influence, you could follow this trajectory. So the pericenter distance will diffuse up and down along this line, but once you hit this green line, gravitational wave emission takes over, and the orbit circularizes and shrinks until you reach the tidal radius. So this process can actually populate this region of small orbits around the supermassive black hole, potentially with periods that are needed to explain the observations. You can also do this simple exercise and calculate what is the eccentricity distribution of stars as they approach the tidal radius on these fairly circular orbits, on these fairly tight orbits. And it turns out that there's sort of a typical eccentricity of roughly 0.1-ish that you get from this process that I described. And that's a result of, and the reason that you don't expect to have very low eccentricity is the fact that there is actually a small number of stars around here that will undergo this trajectory that produces very low eccentricity orbits. And to get very high eccentricity, you need some fine tuning with respect to this critical line, such that you will not get a tidal disruption event, but you can actually start to circularize and reach this tidal radius with some high eccentricity. So that's sort of a general statement that ends up giving you a typical eccentricity of about 0.1.
Was I not all relevant here?
Was I read off? Between what and what?
Well, between some perturber and the trajectory.
Sure. I mean, this is a very simplified picture. You can add more complications onto it, but I think at the 0th order, if you want to explain how do you end up with stars on relevant orbits, then it will be something along these lines. Taking this question of Quasi-Linial to mention binaries, the binaries will actually possibly be important for the generation of these orbits that I mentioned. So the Hills mechanism is what happens when a binary that starts out at large radii of roughly the radius of influence is being scattered towards the supermassive black hole, and then the binary is being disintegrated. One star leaves the system as a hypervelocity star, and the other star remains bound on a period of order, well, this expression here, but essentially a long period that depends on the initial binary separation. So this process introduces another line, or you can think of it as a line of injection of stars that go all the way from the radius of influence to here. So this is the line on which the star that survives the Hills mechanism is formed. And then these stars that are being injected here undergo a similar evolution of two-body relaxation or resonant relaxation until they reach this gravitational waves line and also produce these stellar EMRIs or stellar inspirals. Okay, so one can estimate the rate of each of these events. So I mentioned this before, but the TDE rate is essentially dictated by the orbital period at the radius of influence. So that gives you this typical number of 1 per 10,000 years. The production rate of these inspirals through this single scattering mechanism that I mentioned reduces the TDE rate by this fraction of the gravitational radius divided by the tidal radius squared. So that reduces it by a few orders of magnitude. But if the Hills mechanism is important and you have some binary fraction, here I estimated it to be of 0.1, then you get a production rate of about 1 per 100,000 years. So the overall conclusion is that the number of stars that you would expect to be on orbits that are of order the tidal radius around the supermassive black hole is of order unity, maybe 0.1, maybe 10, but it can't be too low. And that's sort of the argument as to why there should already be a star on a relevant orbit before the TDE occurs.
So you put the like 10% binary fraction, so in this picture, do you require a certain range of the separation for this?
So actually, it's not very sensitive to that. As long as you don't have some preferred binary separation, if the binary separation is, say, log uniform, then all these different scales will contribute similarly to the production of these. Yeah, I mean, if you include the details, then sure, yeah, you would probably have a more complicated distribution, and some binaries will contribute to forming these objects and some will not, but I think it's not very sensitive on the details. Okay, now let's discuss the emission mechanism. So we need to assume something about the disk that the TDE forms. So obviously this disk evolves in time, but for the purpose of calculating the emission at a given state, we assume something about the disk. So we assume that this is a geometrically thin, optically thick, radiation pressure dominated disk with some radiative efficiency. So this may be a fairly simplified picture of what the disk is, but we need to start with something. So we assume these values. And one thing that this picture can explain very naturally is this behavior of long, short alternating flares. The reason is that if you have an orbit that is slightly eccentric, and we already justified this eccentricity, and is highly inclined with respect to the disk, then you would have short separation between the flares as the star passes through pericenter, and long separation, long recurrence time when it passes through apocenter. So that can very easily produce these variations. And in general, the difference or the scatter around the mean periodicity will be related to this eccentricity. So eccentricity of 0.1 actually fits the observations quite nicely. There will be an additional effect in this picture of some light travel effect, which it will be of order 5% of the flare recurrence time. So in a more careful analysis, this should also be accounted for because it's of a similar magnitude to the first process that I described. Okay, so in the time I have left, I'll say something about the emission mechanism itself. So the picture is that the star plows through the disk. It shocks a certain layer of material with a certain mass that is for the typical values that we pick for the 10 to the -6 solar mass. And it accelerates it and heats it up to velocities of about 0.1 c. That's the Keplerian velocity of the star on a given period. The effective cross-section is essentially the geometric cross-section of the star. There's no gravitational focusing involved or anything of that sort because of the collisions are so supersonic. And then as the star plows out, you get this expanding ejecta. And it actually turns out, this was surprising, but this ejecta is almost symmetric from both sides of the disk. I mean, we didn't have any good reason to guess this initially, but we saw some similar simulations in the literature of collisions with an AGM disk that sort of motivated us, showing that you get this almost spherical ejection from both sides of the disk. You get this cloud of moving ejecta.
How do you calculate this? Are you doing this? Are you simulating this?
No, this is, well, which part? There's no simulations. Everything here is sort of.
You produce this picture on the left.
This picture, this is a cartoon. Yes. If it wasn't clear, this is a PowerPoint cartoon of what we think happens there. But as I said, we motivate this by these different simulations that study this problem from the hydrodynamics. Now, initially, this material is very optically thick. It has an optical depth comparable to the disk vertical optical depth, something like 10 to the 4, 10 to the 5. So the radiation is essentially trapped within this ejecta and cannot escape. So the criterion for this emission to first escape is that the diffusion time of photons will be comparable to the dynamical time over which this ejecta cloud evolves. And if you look at this criterion, essentially you find that the peak luminosity occurs once the optical depth goes down to something of the order of C over V, so of order 10. And if you write down how the optical depth evolves as this cloud of ejecta expands, then you can find what is the peak timescale. Turns out to be of order 15 minutes up to an hour, depending on the assumptions. This is also consistent with the rise time that I mentioned before for the flare duration and light curve. But during this time, as the ejecta cloud expands, you suffer from adiabatic losses. So all this internal energy is being cooled down through this adiabatic expansion. And then you get some remaining internal energy at the time of peak, and that gives you a certain luminosity, which turns out to be, I mean, I'm cheating a little, but it's not too different. Turns out to be similar to the Eddington luminosity of the central black hole times this ratio of R star over the semi-major axis. Turns out to be of order 10 to the 41, maybe a few 10 to the 41 ergs per second. This is slightly dimmer than what we would have expected. There may be some factors of order unity that we're missing in the calculation, but this is one point that is not perfect, but we're still quite optimistic.
But why is this related to the Eddington luminosity?
It's not, it's not that trivial, but it goes back to the fact that the disk properties and its optical depth are related to, to whatever is dictated by the black hole, right? A lot of the properties of the disk are related to the property of the black hole. And, it's not very surprising if you assume the same opacity and so on for everything there, that eventually you end up with some dimensional quantity that is the Eddington luminosity of the central black hole. I can show you the calculation. I was also very surprised to see this at first, but it's a nice, cute result that comes out here.
When you allow this star to fly through the disk,
Yeah,
you get these quasi-spherical lobes, like this blob on one side and this blob on the other.
yeah, as I showed here.
All your calculations are,
Yeah,
and so this is motivated by these simulations.
yes.
Can you say a bit on how uncertain the properties of the disk are? Because that depends on your TDE.
Right, so
I'm wondering how much.
So it evolves in time, and that means that the flare properties also evolve in time. I'm sorry, I'm showing you a fiducial property. Yeah, you might expect the flares to brighten or dim as the TDE disk evolves, but let's take it for a fixed disk.
You also see like infrared or UV or optical emission, like you predict
From the observation side. So the observation actually don't show any counterpart to these X-ray flares, but probably the reason is that this is contaminated by the galaxy itself. So these quiescent galaxies are very dim in X-rays. That's why you get this very nice contrast between the flares and the background galaxy. But in all other wavelengths, probably the disk outshines these flares. But yeah, we can make predictions, but it's not clear whether this will be easy to be observed. Okay, let me move on. From these values that I mentioned, you can estimate what's the temperature of this flare. Turns out to be way too low. And actually, when we found this 10 eV, we almost decided to ditch this idea. I was still sort of optimistic because this long, short alternating behavior seemed so profound that, and I couldn't think of a different way to reproduce this. But then we looked into this a bit more carefully, and we realized that in order to get this black body temperature that we estimated, you need to assume that you're in thermal equilibrium. And for that, you need an efficient photon production. So at equilibrium, there will be a certain photon number density corresponding to the black body temperature. And you can calculate what is the ratio between this required number of photons to the rate at which photons are produced through free Bremsstrahlung emission and Compton scattering. And it turns out that for the values that you would assume, you find that this system is actually out of thermal equilibrium. So there aren't enough photons to actually produce the black body radiation. So you have fewer photons that share the same energy density. And that means that each photon is actually more energetic than what the simple black body radiation would assume. And that actually boosts your observed temperature by a factor of 10 or even more. And that actually fits with what we're seeing. So that was a good development for this model. Another thing that you need to make sure is that the hole actually can close before the next passage of the star. So this is easily satisfied either because simply the material just fills in this gap, or because the hole is being sheared, because of the Keplerian motion of the disk.
That's just the asymmetry between the upper part and the lower part. It's something that.
Yeah. So we can't really model that well the difference between these different lobes. You know, we sort of relied on these simulations just to get us to tell us that there are these two lobes, but we can't say, oh, this lobe is denser by 25%. We're not at that level. I mean, it's true that depending on the observer angle, you might be seeing lobes of one kind and then the other kind that may be related to this difference between bright and weak flares, but we don't really know at this stage. So another sort of implication or prediction of this model is that you'll be able to probe the precession timescales, because these will change as the orbit precesses. This will change the relative timing between the flares. This is something that actually this paper has looked into and tried to analyze the timing of the flares. And it sort of seems to be consistent with what we were saying as well. That was another good sign. I mentioned before this qualitative behavior of how the hard bands peak first and decay first. This is again consistent with what we would expect from studying supernovae when you have this hot cloud of material that expands and cools. So I'm showing here again just to give you this impression. You can see that here it's an optical, but the same idea goes to the X-rays. So the hard bands, the UV bands actually peak first and decay first relative to the infrared. This is this overall behavior that we're seeing in the QPEs.
Why don't you go above 1 keV?
Why don't we?
Go above. I mean, you have data above 1 keV.
Oh, I mean, that's the Rosetta band.
The other XMM Newton and you go.
Yeah, so I showed before the spectra, they're actually cutting off. So I said, yeah, the temperatures of, a couple of hundred EV. So the peak is at, say, 3 times that. So below KeV, there's essentially not much emission. Okay, so that's maybe a summary of the successes or failures of our model. One thing that this doesn't naturally explain is these highly irregular flares. Maybe this is another mechanism, maybe something completely different. Yes.
Why do you need a TDE disk instead of just a regular AGN disk?
Okay, so we want to explain this association between the QPEs and TDEs, because in some systems we are seeing that QPEs appeared after what seemed like a TDE. So that's one motivation. It's true that in principle, you could have just a regular disk. I think there are some indications that for most of these systems, they don't show signs of long-term AGN activity. They don't have broadline regions or infrared excess and so on. So it's not clear that there actually was a disk predating the QPEs, or at least not a substantial disk. But yeah, in principle, it could be that you would get something similar with.
You could turn the question around and ask why wouldn't you expect to see these flares in AGN disks, because the stellar dynamics that produces these stars would be the same, and you have lots of gas around.
Right. I think, yeah, it's a good question, and I think part of the reason is that you could ask what is the so this is something I haven't touched upon, but as the star interacts with the disk, eventually its orbit will change because of drag with the disk and because of ablation that it experiences at each of these passages. It turns out that the disk will actually be gone, or sorry, the star will be destructed within a decade or so. So you don't want this disk to be too long-lived, because otherwise this EMRI will eventually be gone. So I think this is maybe a clue as to why we don't expect to see these in regular AGN disks. Okay, so yeah, so these are some topics that they didn't discuss, and I'll just leave here a short summary, and I'll take more questions. Yes.
Is the duty cycle for the irregular ones less?
Nothing distinct. Actually, I think for the first system that I showed way back there, it actually has the longest duty cycle. So that's this 30% duty cycle shown here. This is one of the irregular ones. Why were you thinking of?
If you have a lobby disk or something, and then I don't know.
Yeah, I was trying to imagine maybe there's some weird geometry and the orbit processes so hard that somehow you produce these very irregular flares that. Yes.
So if I look at your picture of the TD, I don't know if this is a cartoon or not, the distribution of the material.
Yeah.
It looks very irregular. So, and I presume the typical timescale of this going around is not so different from the star going around. Could it be that you cut different parts of the material as you go around, if you're far enough that the thing is very something like that? Or is it always a disk and that cartoon is?
Well, yeah, you shouldn't take the cartoons too seriously. I think that the picture is that, I mean, there's this whole question of after a TD, how does circularization actually occur? How does it take place? On what time scale? It's not so clear. But I think the emerging picture is that you have this fallback on initially very eccentric orbits. And then after some time through shocks or some other process, and possibly the GR precession of the streams, material begins to circularize, and then you form a disk, which is actually with a radius similar to the tidal radius. That's why we also need these objects to be not too far from the tidal radius to interact with this disk. So I mean, my picture, in my mental picture, is that this disk is actually quite regular at this stage, but it is possible that, you know, the picture
So
is
in the
more
lifetime
complex.
of this disk, what's the fraction when it is regular compared to when it is still a crazy?
Yeah, so we can say something from TDE observations. So assuming that this long X-ray emission comes from the disk, which is, I think, reasonable, then it lasts of order years. That's again related to this question that Jim asked. We don't want this disk to be there for too long, because then the star is eventually ablated or being dragged significantly.
Yeah.
So this might be super silly, and you might have explained this, but at the beginning of the Scott asked you a question about the radius, and he said that it, in some cases, it was less than 1 RG. And then
The emitting region.
the emitting reading. Okay.
Yeah.
I thought it was,
No.
okay, that was my question. Thank you.
Okay, yeah, and I have to say that sort of, given what I said about this photon starvation, you can't really interpret the emission purely as a black body radiation. So the radius that you get is actually off. It's more like a Armstrong spectrum. So. Yeah.
So basically for this star disk collision scenario, basically is that you have a disk and you happen to have another star that's close enough to have this QPE.
Right.
And my question is that, so because most of the TDE actually don't have these QPE afterwards. So the reason for that is just because there's just no nearby star that's close enough to have that collision. And it's not consistent with like the number density of star around the central region.
Yeah. So we are sort of still debating about the question of whether this could be a very strong statement saying that every TDE should have QPEs formed. I think in reality it's more complex, and you would need the second star to form a disk that is wide enough to actually intercept the stars, the EMRIs orbit. So that might say something about what should be the mass and the properties of the second event or the TDE that forms this. In terms of the rates, it's kind of hard to say, but I think that we're roughly consistent with what is being observed. I mean, the rate estimates are also quite miserable at the moment, because we only have 4 systems and only 2 of them were detected with what is sort of a blind search. So I think that the current estimates is that QPEs in terms of abundance occur at roughly about 1 per 100,000 galaxies. And if you look at the numbers of what I said before about, the rate of EMRIs and the rate of TDEs and so on, it sort of seemed consistent, but we're still arguing that.
So what is your best guess for the irregular sources? Is it another model, or is it, they do seem to be?
Yeah, it's a good question. I think, okay, one thing that you can't really ignore is the emission properties of these different QPs seem fairly consistent with one another. So invoking a completely different mechanism is probably not very likely. One model that I proposed in the past involves a star that is actually being gently stripped from mass as it passes its pericenter, again on a fairly tight orbit around the supermassive black hole. And then you could imagine that you produce streams of gas that then interact with one another. You could imagine how this picture also provides a mechanism that is similar to these collisions. I mean, again, you have some interaction between the star and an accretion flow, but this time it's not with some regular planar disk, but maybe some more complex scenario where you have this spaghetti ball of streams that interact with one another and the star. So it's just a very vague idea, but possibly that's a suggestion. Yeah.
Maybe a stupid question. Suppose the data got much better. You got thousands of these and for a long time, and you said that you could tie the sort of modulation in the period to like lens steering precession. Yes, this starts to become a very good test of GR.
Right. Yeah. I think so. I haven't had time to talk about this, but I think the prospects for what we can learn from QPEs are actually quite interesting. So this is one example, what you mentioned, studying lens steering precession, and through this the spin of this population of black holes. Another thing that this can teach us is about the rate of EMRI production, because essentially what we're probing here in this model is exactly stars that have been brought close to the supermassive black hole and will eventually inspiral towards it through gravitational waves. This is again the same channel that you would get for compact objects. So this is maybe the first observational constraint on EMRI production. That's another sort of consequence. I think that there are a lot of similarities to TDEs in the sense that they occur around otherwise quiescent black holes and so on. But I think what's interesting about these systems is that unlike TDEs that are sort of a one-off event, typically that occur once and that's it. If you got the data, good. If not, wait for the next one. Wait 10,000 years. Here you have this recurring behavior where every few hours you have more data.
So many orbits.
Right, so many orbits, and you actually probe very small distances around the supermassive black hole. So yeah, I think the potential is huge, and we're just starting to see the tip of a much bigger iceberg.
I have a naive observational question. Like with Rubin, you would see like a lot more TDEs than now. Like, can you follow? Like, what's the bottleneck observationally? Can you follow up with X-ray those many candidates?
Yeah, I think so. Currently, we don't have these big X-ray surveys. I mean, Eero-Zeta is the best, and it's also not really dedicated to this sort of large survey that you're describing. I mean, you can follow up with XMM Newton and other instruments, but yeah, I think in the future we'll need more instruments to complement these bigger optical surveys.
Okay, no more questions for Itai. Let's thank him again for the nice talk.